just write the molecular equation first. H3PO4 is phosphoric acid. Potassium hydroxide is KOH. What kind of reaction are we talking about here? Is it single displacement, double displacement, decomposite? What kind of reaction is this?
Double displacement.
Double displacement. Okay, so which means that we're going to take the H3 over here, combine that with the OH, and take the PO4 and combine that with potassium hydroxide. Okay, so that's what we have to do with the double displacement here. H3 and OH, what will that give us? Please help me out there.
Yeah?
What will the hydrogen over here and OH give me? H2O. Okay, that's it, just water. All right. The H3 has to do with how many hydrogen ions we have. Okay, and so that's a different thing. We'll talk about that in balancing of the equation. All right, and the formula for this is this correct?
No, K3.
K3, okay, very good. So because PO4 is 3 minus, all right, so make sure your formulas are correct. Only then you can balance your equation, and you have to learn how to balance equations because we will still be doing stoichiometry. Okay, so you have to learn how to do all of that. Nomenclature is by far the hardest thing always. It's not the hardest thing, I should say. It's the hardest thing to keep up for some reason. Okay, even in the exam, that was the main thing. Okay, it's not like you don't know how to do problems. You know how to solve problems, you just don't remember nomenclature. Okay, and that should not be the problem. Okay, so that's that. Let's go ahead and balance out the equation. We need 3 over here, correct? All right, and then
3 in front of water.
3 in front of water. All right, now for the states. Okay, so H3 and PO4, because this is an acid, this is going to be aqueous. Potassium hydroxide, also aqueous. K3PO4, potassium phosphate. What do you think? For this, you have to know your solubility rules, and potassium salts are all soluble, right? So if you have anything aqueous in there, then potassium salts will be soluble, and then water is, of course, liquid. Okay, that's not going to be aqueous. So that's your molecular ion equation. And I just want to go on with the ionic equation also here with you in case you've forgotten. So here, this will be what? Go ahead and help me out here, please. I will write H3 as what for ionic equation? 3H plus, right? Okay, because I have 3 hydrogen ions here, so aqueous plus phosphate, 3 minus, aqueous plus, and then I have 3 of the potassium ions, and I have 3 of the hydroxide ions, all of them in aqueous solution. And then here, since my potassium phosphate is aqueous, now I have 3 potassium ions, 1 phosphate ion, and 3 water, which does not dissociate because it's a liquid. My spectator ions are, what are my spectator ions here?
Potassium.
And phosphate, potassium and phosphate. So when I write my net ionic equation, it's going to be the 3H plus 3 hydroxides to give me 3 waters. Okay, that's how it's going to be. Please do not let it go because this is, the main part of the first part of this chapter. So please keep practicing. This kind of equation, again, this is an acid-base equation. This is neutralization reaction. One of the properties that I think I missed out in telling you when I was talking about the acid-base properties is the pH, okay, of acids and bases. If you want to go back to where I gave you the properties of acids and bases, you may want to add that, okay, to there. And this is to do with the pH, which you will learn again more in GenChem2. But for acids, the pH is 0 to 7, and for bases, the pH is 7 to 14, which means the neutral pH is a wonderful 7. Okay, so anything below 7 is acidic, Anything above 7 is basic. Okay, and so when we say we have neutralization reactions, it technically means that now you have a pH of 7. Okay, because neutral is 7. Okay, at that point, which sometimes is a lie. It doesn't always hold true. Okay, which when you get to GenChem 2, then you will learn a little bit more about that also. Okay, as to why that's not true. All right. Then another reaction. Sodium hydrogen carbonate and hydrochloric acid. Go ahead and write this out too, please. I'll give you 30 seconds. Sodium hydrogen carbonate, sodium hydrogen carbonate. Okay, that's the formula. And then we have hydrochloric acid, which is HCl. Since we're talking about aqueous reactions, let's go ahead and put AQ. AQ. And then the products, again, we have a double displacement reaction. So sodium is going to combine with Cl to give you sodium chloride. Is that soluble or insoluble in water? Soluble. Okay, very good, thank you. And then you also end up getting the HCO3 and H. This is a polyatomic ion, and you don't separate that out. Okay, just like over here, we did not separate out the phosphate. We left the phosphate the same on the right-hand side. So here also, right now I'm going to leave it as the same. So this is H2CO3, which is combining HCO3 with HCl. And H2CO3 is also aqueous. Now here's the difference between the first reaction we wrote out and the second one, which is why I'm writing this one out. There's something different about this. What you end up forming here is carbonic acid. H2CO3 is carbonic acid. Remember I just said about 5 minutes ago that when we say we have neutralization reactions, it's really quite a lie. Here's the lie right there, okay? Because you're forming a carbonic acid as a product, okay? Which means that you didn't really neutralize anything. But here is what happens really with H2CO3. You don't really get carbonic acid as such. If it's a weak acid, you end up getting H2O and carbon dioxide. Okay? So essentially what you have as products is NaCl plus CO2 plus H2O. These two actually combine to give the carbonic acid. So I took the simple route first by doing the double displacement and then telling you how it really works, okay? That you don't really have carbonic acid, you actually have carbon dioxide dissolved in water, so which means carbon dioxide here is a gas and water here is a liquid. NaCl, of course, was aqueous, as you said before. Last week I had introduced the concept of evidence of chemical reactions. How do you know a chemical reaction is taking place? And the first one was precipitation. So we've done all the precipitation reactions already. And then second one was effervescence. Okay, and right here is effervescence. So which means that if you take something like sodium bicarbonate and add HCl to this, then you will end up getting a gas in there. Okay, carbon dioxide. And this is the classic formula for making volcanoes, right? So except for HCl, you would use acetic acid if you were doing it at home, because at home you won't find acetic acid, HCl anywhere. Okay, so at home you take baking soda and you add acetic acid to that, and you will end up getting all these bubbles and everything. Okay, and so that's effervescence there for you. When you have to write an ionic equation for this one, you will keep the H2CO3 like this. Okay, so which means that your final ionic equation is going to have HCO3 and H in it, okay, as your ions in there. Okay, that ionic equation. I'm not going to do it here. You're going to finish it at home. Okay? Yes.
So for the molecular equation, do we break it up or leave it as?
No, break it up like this. This is the correct one. Okay? I just did the simple thing first. Okay? By just doing the double displacement, so you don't have to think. There are a few compounds that give you gases. So the first equation there, the phosphoric acid and potassium hydroxide, doesn't give you any gas. There is no option, there is no place for it. Okay, the chemicals you're using there are pretty simple, so you don't see any gas formation. But here the compound is such that it will form gases. okay, for you. So here, the carbonate, the hydrogen carbonate, carbonates, sulfides, they all give you gases, okay, in their reactions. So there are few compounds that will give you gas reactions, okay. And so on page number, I'll tell you, 145, okay, go through that if you want. And on this one, there are some more reactions, okay, which you can look over to see that you have gas reactions also, okay. All right, any questions? So precipitation we've done, neutralization we've done, now for redox reaction. I don't know if I've mentioned this before, but I'll go ahead and say it again. This chapter in GenChem 2 is like 5 chapters, okay? So it's really quite humongous. What you're doing here is like just the tip of the iceberg, okay? So it's just quite a big thing in there. So redox reactions, redox, reduction, oxidation. So the first thing we'll do is see what is oxidation and what is reduction. The nice thing about oxidation reduction is that they are completely opposite of each other. Acids and bases are not completely opposite of each other. Okay, you still have to know the properties of each of them, but redox are. Okay, they're completely opposites of each other. So first, very simple one, oxidation is addition of oxygen. So which means reduction is then removal of oxygen. Reduction is addition of hydrogen. So oxidation must be then removal, of hydrogen. This is all well and good if you have oxygen and hydrogen in your reaction. But if you don't have oxygen and hydrogen in your reactions, or there's no way for you to figure it out, then you need some other way. And the last definition is then the electronic definition. Okay, it's the give and take of electrons, because in almost all reactions you will have some sort of give and take of electrons. So oxidation is then loss of electrons, and reduction would be then gain of electrons. I'm really not so much into mnemonics, because when I studied, I don't know if mnemonics was there or not. I think it was there. There were a few things we did by mnemonics, but for this one there is one, okay, and that is LEO and GER. Leo goes GER, I don't know, anyhow. Loss of electron, oxidation. Gain electrons is reduction. In case you're having a hard time remembering this, there is another one. These are all things that I learned in America. Oil, rig. Oxidation is loss, reduction is gain. Whichever turns your fancy. I prefer lions. All right, simple equation first. You've seen this before. I don't know how many times I've used this equation. Carbon plus oxygen to give carbon dioxide. One thing is true for oxidation reduction reactions is that if one thing is getting oxidized, something else must be getting reduced. Okay? It's always a give and take. It's never going to be that you only have oxidation going on. That's never going to happen. Okay? So here, it's a very simple thing, right? Because you have oxygen present over here. So what is getting oxidized? The carbon, because carbon is adding on the oxygen. Okay, so carbon is getting oxidized, so oxygen must be getting reduced. Okay, it's the opposite then. So you don't have to think too much about it. Once you know about the one, then the other one is obviously the opposite of. And by the way, the same goes for oxidation and reduction definitions. Just remember one. Okay, the other one is totally opposite of it. Okay, so no need to memorize both of them. Don't tax your memory. Okay, just one is enough. I usually just remember oxidation, and then reduction comes naturally. Okay, because it's complete opposite. Okay, so that's one kind of a reaction where you have oxygen present. Here's another kind and that would be reduction reaction then, because you're adding on hydrogen. Okay, so one is an oxidation reaction, one is a reduction reaction. If you wanted to get into specifics, okay, as to what I was asking before, when I said carbon is getting oxidized and oxygen is getting reduced, carbon is getting oxidized, we understand. Okay, sure, because it's adding on oxygen, but how is oxygen getting reduced? Okay, that's a little bit of an iffy thing. When you look at this, it's kind of hard to see how oxygen is getting reduced. So for that, we'll have to go to the electronic part. Okay, so you can't do everything by everything. Okay, so you just choose whichever definition suits your needs and you work by that. Okay, so let's talk a little bit about how the electronic thing works. Okay, so for electronic thing, before we get into that equation, we need to go over what is called oxidation numbers. And oxidation numbers are the charges that you would have on any element. On the alum lab, there was a question about valency, right? What's the valency of 3 and what's the valency of 1, right? If you remember that from your pre-lab. And a lot of you actually wrote, at least in my lab, I got a lot of answers like, it means it has a valency of 3. Well, that really answers my question, because it doesn't. Okay, what does it mean that something has a valency of 3? That it is capable of bonding with 3 electrons, okay, or bonding with 1 electron. That is what valency means, okay? So it's bonding with 3, it's bonding with 1, bonding with 5, so it could be pentavalent, okay? So that's valency. Valency in some ways is also oxidation numbers. You already know a few of the oxidation numbers. I gave you those. So for example, in group 1, the charge is +1, okay? And it will always be +1, okay? That's what we had decided. Because it's group 1, main group element, the valencies don't change that much, okay? Or the oxidation numbers don't change that much. So group 1 is +1, this is +2, going on to 3, and then this is ±4, okay? So it can be either of those, and then -3, -2, -1, okay? That's how it is. Usually when we do oxidation numbers, they're going to be positive numbers, but they can be negative also, okay? Because in some cases you have to work with negatives. All right, first rules of oxidation numbers is that elements in their natural state have oxidation number 0. So elements in their natural state means that they're not combined with anything, okay? So any kind of an element like a metal, for example, if you have lithium, sodium, magnesium, iron, gold, all by itself, existing by itself, not combined with anything, the oxidation number is 0, okay? That's what the one rule is. Then the natural state for non-metals, okay, that would be the diatomic gases. So for example, N2, O2, Cl2, H2, wherever you encounter these gases, which is how they exist on the earth. So I gave you 7 gases or compounds before that exist as diatomics, that will be 0 then, okay? And then if you have something really odd looking, like P4, which really, what is P4, all right? And we'll talk about that when we get to chapter 7 or 8, to remember which one it is. But if you have P2, P4, P6, something like that also, just by itself as an element, okay, that also is going to be 0, which means it's not combined with anything else, okay? So an element combined with itself is because that's how it exists in the natural state. So all of these ones are 0. Okay, over here as far as oxidation number is concerned. Let's take a simple one first. If I write NaCl and I ask you for the oxidation numbers for both of them, you would say Na is +1, Cl is -1. Okay, that's the oxidation numbers. And that's pretty easy to do. Okay, not hard at all, because you know that from the periodic table. For transition metals, you have to calculate. So we did this a little bit in chapter 2 when we were going through nomenclature, okay? Because for transition metals, the valencies can change, okay? Because depending on how many electrons are being given by the metal, you can have different charges, okay? So iron can be +2, +3, chromium can be 3 or 6, okay? Depending on what it is combining and how it's combining. So here, iron is going to be +2, because oxygen is -2, and oxygen doesn't change. Okay, there's only one compound where oxygen is going to change, and that is peroxide, which we will work out, okay, later on. But for most part, okay, for oxidation numbers, you always start with something that you know, okay, and then you work your way backward, okay, from there. So for example, Cr2O3. Let's work on this one. So find me the oxidation number for chromium. So start with oxygen. Oxygen is -2, and then you have 3 of those, right? So that's a total of -6, which means chromium must be a total of +6, because it's a neutral compound. And how many chromiums do we have? 2. So we divide this by 2, and then each chromium is +3. You would do the same thing if you had to name it also, okay? Because then this is chromium 3 oxide. So that 3 was actually the oxidation number. Okay, so now we know how to calculate oxidation number for this. Okay, not bad at all. Then let's go on to something like this. Yes?
On the chromium, it doesn't matter if it's Cr2, the oxidation number is going to be positive. In there, it's going to be +3.
It's going to be +3. So are you worried about there being 2 chromiums, or are you worried about, yeah? Okay. So when you calculate oxidation numbers, it's for an individual atom, not together. Okay. So now when you calculate for nitrogen, it's going to come out positive, okay? But technically when we talked about numbers, nitrogen was actually -3, right? Okay. A -3 would be if it was combining with a non-metal. But now it's actually combining with a non-metal. It's a covalent compound. And because it's the first element, it has to be positive. Okay? First elements are always positive. The second ones are always negative. So which means that oxygen here is still -2. So nitrogen here must be then +1. Okay? And so this is +2. Divided by 2, and that is +1. Okay? And nitrogen, if you remember from a long time ago when we were doing the nomenclature, it has so many oxides, right? Nitrogen monoxide, nitrogen dioxide, trioxide, and so on. So nitrogen can have a variety of oxidation states. Okay? And the same thing goes for chlorine also. Okay? It can have variety. Let's do a polyatomic ion. Let's say we have this, which is potassium sulfate. And if I ask you to calculate the number for sulfur. So now you have 3 elements to work with. Now you can't take sulfate as a total sulfate. Now you have to deal with each element, okay, separately. So here, oxygen is still -2 times 4, right? Potassium is +1 times 2. That's not going to change. Okay, potassium, group 1 and 2, they will always stay the same. Okay, group 3 might change because of the metalloid, okay, which is boron over there. So that it might change a little bit, but in general it will not also. What was your question?
Does it become positive, the sulfur?
What becomes sulfur? Does it become? Well, we'll find out. Okay, and if you've done it already, then great. All right. So sulfur is what we are trying to find out here. Okay, that's the X. Depending on how you work this out. Okay. Eventually you'll be able to do this very fast. Okay, and even now, I mean, I don't think this is very slow. So this is a total of -8. This is +2. And the total charge here is actually 0, right? Because we're dealing with a neutral molecule. So if it's neutral, the total of everything should come out to be 0. So X must be +6. So sulfur is +6 over here. So yes, Anna, you were right. Okay, but then make sure you work it out, all right? In general, only the last element is going to be negative, so that's a big clue, okay, right there. So only the last element is going to be negative, so which means everything else must be positive then. Good so far? Okay. One more, last one, and now this one actually has a negative charge left over, which means that by the time you do the total, you should have a residual charge of -1. Okay, so go ahead and do that for chlorine. 1.
Plus 5 then?
Plus 5, okay, so this is -2 times 3, -6, and this must be plus 5 to give you -1. How is that hard? How is that not doable in 30 seconds? I did that in under 10 seconds. No, I know how to do stuff, okay, but how is that not doable in 30 seconds? Yes?
Where are the numbers coming from?
Where are the numbers coming?
Yeah, like I don't see that at all.
Oxygen, where is oxygen in the periodic table?
Oh, okay, I see the 2.
Okay, that's where it's coming from, and the 3 is coming from right here because you have 3 oxygens.
Oh, okay.
So that's where that number is coming from. This is what you're calculating for. So yeah, you just calculated that. Okay, all right, good.
The negative lets you know that you have negative 1 left over.
Yes. Okay, so for example, if you were calculating for phosphate, for phosphorus, then you would have 3 negative left over. Okay, so here, let's do this really quickly in 5 seconds. No, don't write, just look. Oxygen is -2 times 4, 8, and this must be then plus 5. Got it? 10 seconds, done, moving on. Okay, yeah, it shouldn't take you this long, okay, to do some of these things. Oxidation numbers are easy. Okay, let me come back to this equation over here with carbon dioxide. So we established the fact that carbon was getting oxidized, okay, because it was adding on oxygen. Now we're going to do it electronically, okay, and see what's going on. So carbon here, what's the oxidation number? 0. For oxygen? Also 0 because these are elements, okay, so you have 0 oxidation number. What's carbon over here?
4.
Not just 4? Plus 4, and this is total of -4, okay? But you know in your heart that each oxygen is -2, okay? So you're looking at the totality here. Okay, so electronically speaking, what has lost electrons? Carbon went from 0 to +4. That is loss of electrons, right? Okay, so there, loss of electron, and loss of electrons is oxidation, okay? What has oxygen done meanwhile? It gained electrons, right? Because it went from 0 to -4, and so that is gain of electrons, and so that is reduction. So something that was not very obvious as to how oxygen would get reduced, now is very much more obvious. Okay, so electronic really is the best way to go when you're doing redox reactions, but it depends what's available to you. Okay, I always take the shortest route. I don't have to go by electrons if I have oxygen and hydrogen present. Okay, we'll do some more reactions then. So here is a reaction we wrote out a while back. And help me out. Okay, participate please, little bit. So zinc, what is the state I should write here? Solid, liquid, gas, what should it be? Solid. Okay, this is just a plain metal, so it should be solid, okay? And HCl should be aqueous. Zinc chloride should be solubility rules, still not there yet, okay. Know your solubility rules, okay? That will tell you that zinc chloride, almost all chlorides are soluble except for the lead, mercury, silver, those kinds, okay? Those are the ones that are insoluble. All others are soluble. And then hydrogen is gas.
There should be a 2 for every HCl, right?
There should be? You think there should be? Okay, all right. Because
Because that way.
You want to balance the equation, okay? And that's fine, okay? You should have that. You should also let me finish.
Sorry.
It would be great
I
too,
didn't
but
want you to
okay.
get too far before it.
Okay, all right, no, just wait a little bit, okay? Yeah, just wait for 30 seconds, okay. This is a similar reaction that you did in your alum lab also. If you remember when you took the aluminum and you added KOH to that, boom, 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 there was a whole lot of gas formation in there, okay? So it's similar kind of reaction. So metals will react both with acids and with bases also, okay? And giving out a lot of hydrogen gas. So this is a reaction that's going on here. So go ahead, take about 30 seconds, again, not too long, and tell me what is getting oxidized and what's getting reduced. If you want, you can write an ionic equation first. Okay, let me help you with the ionic equation. Zinc, solid, plus 2H plus 2Cl minus. Don't forget, okay, that the 2 belongs to both hydrogen and to the Cl, okay, to both of these things. And then you have zinc, 2 plus, aqueous plus 2Cl minus. And again, the subscript comes up as coefficient, and then you have H2 gas. And now I will leave you alone for about 30 seconds, and you tell me what is getting oxidized and what is getting reduced.
Are we going to go over the agent, reducing agent?
We don't. Yeah. Because at this point, it's a little confusing sometimes because it's the opposite.
Mhm.
You know.
I like doing it.
We do it. You do that in your session, no problem. It'll be great.
Okay.
Yeah. Okay, Jeffrey, what's happening to zinc?
Like,
What's
why does
happening
it
to
go to
zinc?
2?
What?
Why does it go to 2 on the right side?
Why does it go to
Is it
2?
because it's not, it's aqueous now, not solid?
That's the charge on this because here you have chlorine, which is,
Right.
each of them
Oh,
is? Okay, all right. Yes, fine. What's happening to zinc over here? Is it getting oxidized, or getting reduced? Oh my God, confidence, we're missing that, Dominic. Say it with confidence for me.
Getting reduced.
It's getting reduced? Zinc?
Yeah.
Okay, I'm not getting the right answer. What's happening? What happened to zinc here?
It got oxidized.
It got oxidized. Confidence, please. Okay. You don't even have to think that much. Zinc is losing electrons. If it's losing electrons, that is oxidation. Okay? Should not be taking you this long to do this.
Do you need the ionic formula to do this? Or can you just look at the fact that
You
Cl
can
is
just look at the
losing
equation.
hydrogen?
I was just helping you guys out. I was just helping out, that's all. Yes. What is my spectator ion in this equation? Hmm? Chloride. Chloride. Okay, chlorine. So here, let's cross that out. So that we're not even looking at it, because if you have spectator ions in there, it means there's no reaction going on, okay? Because they are on both sides. So you just cross those out, so you don't even look at it. So if zinc is getting oxidized, what is getting reduced?
Hydrogen.
That's it. You don't even have to think about it, okay? Because if one is getting oxidized, the other one must be getting reduced then. Which it is because it is gaining electrons. Here it is plus, there it's neutral, okay? All right, don't make this hard, okay? This is probably the easiest part of this chapter, okay? You don't have to remember any rules here. There are no solubility rules here. You don't have to remember any acids in here. All you have to do is look at the equation and then see what's losing and what's gaining electrons, okay? So don't make this hard for yourself. All right, what we do in oxidation reduction reactions is that we actually put them, we split them in half, okay? We split them into what's called half reactions, And in the half reaction, you will have the oxidation reaction separately written out and the reduction, okay, separately written out. So let's do that. So here zinc is going to zinc 2 plus, and then we have the 2H plus going to H2. And zinc is getting oxidized, so this is the oxidation half reaction, and hydrogen is gaining electrons, so this is the reduction part of the equation. These are half reactions. So, it's not done. It's not done yet. Zinc went from zinc to zinc 2 plus. How many electrons did it lose? 2 electrons. Okay, so if it loses electrons, you write that on the right hand side. Okay, because that is part of a product. Zinc going to zinc 2 plus and 2 electrons. When hydrogen ions went from hydrogen ions to hydrogen, how many electrons did they accept? 2 electrons. And then you write that on the left hand side because this is gain of electrons. This equation was balanced out very nicely because it's a simple reaction. So as we were doing it before, you put 2 in front of HCl and boom, we were done. Okay, no problem. It was easy to balance this equation because it was a simple equation. Okay, but sometimes the oxidation reduction equations are not all that easy. So what you have to do is you have to split them into 2. Okay, one of the most important things about redox equations is making sure that whatever number of electrons are lost are also the same number of electrons that are gained. Because if you have an uneven number of gain and loss, it means the equation is not balanced yet. Okay, because you can't have something accepting more electrons than that were given. You see that? Okay, so you can't have that. So we split it into 2 equations, oxidation and then reduction, and then balance out the electrons. Okay, this is something which is really an involved process which you learn in GenChem2. All right, here I'm going to leave it like this, just as half reactions. But in GenChem2, there is a whole process by which you work step by step by step in trying to balance all of these equations. So redox equations, again, gain and loss of electrons. A lot of the redox equations are going to be really weird for us, meaning that you would have decomposition reactions in there, you will have combination reactions in there, sometimes even double displacements, okay, things like that. But one thing is true, that not all reactions may be redox reactions, okay? Some of the precipitation reactions that we work with, they're actually not redox reactions at all, okay? Because for redox reactions, there must be a change in oxidation number. So if there's no change in oxidation number, there is no redox going on. We're good? How are we doing? Yes? Okay. Yes?
I have a question with the oxidation numbers. So I don't understand how some were getting to 0 and the other was +1.
So the 0 ones are in their elemental state, okay, if they're not combined with anything at all. All right, so metals that exist by themselves, those are going to be 0. They're not combined with anything like zinc, magnesium. Here zinc is 0, okay, it's not combined with anything. And then elements that exist by themselves here like H2, that's actually 0. Okay, so diatomic gases, they're all going to be 0. Example I gave you also for P4, there could be S6, there could be C70. All of those will be 0 because they are existing by themselves. Okay, only when they're combined with another element that they're going to have an oxidation number. Okay, the plus and minus have to do with their location, okay, as to where they are. So for example, when you have something like HCl, here hydrogen is written first. So it means hydrogen must be positive or negative?
Positive.
Positive, okay? Anything that is written first is always positive, okay? Now what is hydrogen?
Negative.
Negative, Okay, so it's a very systematic thing that we do in chemistry, okay, so that you're not confused about anything, all right? Do those compounds exist? Yes, both of them exist, all right? But the oxidation numbers on each of these hydrogens is different, okay? In the first one, it's going to be plus 1, because chlorine is minus 1, okay? Here, hydrogen is going to be because sodium is, and that never changes, okay? So you have to find out, and I've given you all of those, not like you have to explore it anymore, okay? So you have it already, which numbers are constant, okay, to work with. Group number 1, 2, 3 are pretty constant. Oxygen is constant, and when you have halogens written as the second element, when you have halogens written as the second element where they are negative, they're always constant, okay, as -1. So you don't have to worry about it, okay? So again, if you have something like ClO3 minus, this Cl is very different from this Cl, right? Okay, so that's how you determine if it's going to be plus or minus, okay? So you have to watch out. You can't memorize this, okay? Don't memorize it. It's not worth it, okay? Good, moving along then. Next topic is concentrations. This chapter really is like 2 chapters, okay, in one. So the first portion is all about writing equations. The second portion is using those equations in some ways, if I can make the connection, and doing calculations, okay? So the first thing you have to understand about solutions is that they have a concentration. So what is a solution? Let's do that first. So solution concentration. So solute plus solvent. I feel like I've done this before. Yes, I have. I think I have. Okay, it's not just yesterday, but yeah. Is equal to a solution. Solute is usually the smaller amount, and solvent is usually the larger amount. And if I have done this before, then I must have mentioned to you that you can have any kind of solute or solvent. Okay, it doesn't have to be liquid or solid, it could be liquid. So now that we're working only with aqueous systems, our solvent is going to be water. Okay, at this point, so we're not dealing with any other solvent right now, although you can calculate concentration for anything, all right? But right now, for us, our solvent is water. Solute could be anything. There are very many different ways that you can calculate concentration, and it's really important, okay, that we actually know how to calculate concentration. So you might have seen this in your lab already when you did the alum lab. That's when we started using concentrations, that you had 6m KOH and 6m H2SO4. Okay, so that M, so 6m, that M there stood for molarity. And of course, since we're all chemists, okay, molarity is moles over liter. That's your formula, because we all work with moles. Is this the only way you can do concentration? No. Okay, there are many other ways. And again, this is a full-blown chapter in GenChem 2. Here we will concentrate only on molarity. So when we talk about solution concentrations, okay, and we say 6 molar solution, 6 molar means that we have 6 moles of something in 1 liter of solution. Okay, so when we go to the lab and we want to make a solution, we will figure out how many grams we will need then, okay, of that. So the moles is a nice way, because the moles tells us how many atoms we have in there. Okay, so once we know how many moles we have, you just dissolve it in that liter of water. So depending on how much you're making, you can make 500 milliliters of solution. You could make 600 milliliters. It depends, okay, how much we need. For us, when we work in labs, and considering how big the GenChem labs are, we're working in 3 liters, 4, 5 liter solutions, okay? So we have to make massive quantities, okay, of solutions. So we just calculate how much we need, and then you go into the lab and you dissolve them, make your solution, okay? So that's molarity, and we will do the calculations next time, okay? On Tuesday, we will not do it today.